Hey guys, and welcome back. I'm going to be teaching you about SPI. So in the last video we spoke about I2C. Now if you want to transfer your data of 8 bits, which can be 10101010 or hexadecimal 0xAA, you just use two wires, which is your clock and data, to transfer the data. Now looking at SPI, which stands for Serial Peripheral Interface, and this is more or less what it looks like. So you need slightly more pins than I2C, but there are added benefits to having this. So first of all, let's look at what we have. So we've got a serial clock, which synchronizes our data bits. We have a master in, slave out, which is also known as meso, and that goes from the slave to the master. We have a master out and slave in, that is mozzie. And you also have a slave select line, also known as SS. So what happens if you have multiple slaves? So now, unlike I2C where you just use the same two wires, over here you need to increase the amount of pins by the number of slaves that you have. So we have the same serial clock, meso and mozzie lines, and you can either connect them in this configuration or you can connect them in a daisy chain configuration like this. So over here you got your master out, slave in, and that goes in from one device, out from the meso into the mozzie, and from the meso out into the mozzie, and out from the meso into the meso. So either configuration is fine, depending on what your requirements are. Let's take a look at the advantages and disadvantages of SPI. So the advantages of SPI is that we have a higher throughput than UART as well as I2C. So SPI has a throughput of 10 megabits per second to around 20 megabits per second, depending on the type of chip that you're using and what they support. I2C generally runs at around 100 kilohertz, 400 kilohertz, and now until recently can move up to 3.4 megabits per second, which is quite fast, but not as fast as SPI. So SPI has a simple receiver hardware. We use a simple shift register. And what's nice about it is that we don't have a rigid transmission protocol like I2C. We can send a bunch of data and we can program the slave to know exactly what to expect. Also, what is nice about SPI is that it supports multiple slaves. Another advantage that we have is that it uses less power than I2C. Looking at the disadvantages of SPI. Now SPI, as you've seen, requires more pins. And if you've got a lot of slaves, then you really need a big microcontroller to handle the chip select of each slave. There is no flow control on SPI though. A big disadvantage is that you can only have one master on the SPI bus, unless you have separate slave select lines for each slave. It can get quite messy in this kind of situation. Let's take a look at the read-write protocols, or data transmission protocols. So if you got a single slave configuration, we can look at, say, an Arduino, which is talking to a slave, which is an EEPROM device. Atmel has a device called the AT25010, and by using SPI, you can really communicate fast with this device compared to I2C. So as I mentioned before, with SPI, every company has their own transmission protocols, and you have to read the datasheets on how to communicate with each peripheral. Slave select or chip select is always low for an active slave. If you make the slave select of all slaves low, then you stand a chance of having conflicting data coming to your master. Now imagine all this data flooding your master from all these different slaves, and therefore we only select one slave at a time. So over here, we start off by putting our chip select or slave select down to 0. Once we initiated that, we can clock in our signals. And while we're clocking our signals, we send our instruction byte. Now this is a specific code which is unique to the chip, and this is a high as shown in the datasheet. Over here we have a 1 and a 0, and this signifies a write. And once we send our instruction byte, we can proceed to send our byte address. So this byte address is where in memory do you want to store your byte. Once you know that, you can store your data, and you can send a 8-bit data to your bus. Just keep in mind that we got our most significant bit over here and our least significant bit over here. Same over here. And because we're not reading anything, our slave output is just in high impedance mode. Let's take a look at the read protocol. Now in a similar way, we put our chip select down to 0 to activate our slave. we're clocking our device with a constant clock at a certain frequency, say around 10 megahertz, depending on the predefined speed of this chip. And then we send our instruction byte. Now this is standard for read or write. And then as you can see, we got a 1 and a 1, if you put this in line. A 1 and a 1 signifies a read. Next, we send over our byte address that we want to read from. So if we send an address of 1, all this will be zeros, and this will be 1. And at this falling edge, our slave sends this data out to the master. And it sends it via the slave output line, which is over here. So as you can see, we got our 0 clock, which is this one. We got our master in slave out, which is this line over here. We got our master out, slave in, which is this one over here. And then we have our slave select, or chip select in this case. This line signifies a NOT. So this is chip select NOT. SPI has different modes that you can select. So we have 4 modes over here. So our clocking position can either be low, low, either rising or falling edge. And the same goes for high, where you can have a falling or rising edge. Now the reason for this is all dependent on your master or slave. So if you have an FPGA talking to an Arduino, or vice versa, and you want to clock it on a low, and you want to clock it on the rising edge of the clock, then you can select SPI mode number 1. So it all depends on the configuration of your device. Now this code is for Arduino, where you can get it at this link over here, but I will put that link down in the description below. So what is happening is that we first transfer our address by the SPI transfer. And over here, if you want to read from the EEPROM, you put your slave select down to low. You transfer the read up code or the instruction code. And over here, we have it as read. Thereafter, we send our address that we want to read from. And then this is the data that we receive. So SPI transfer, which goes into data. And then we return our data back for use. So as you can see, SPI is a very simple protocol. And in my opinion, it's much more easier than I2C. But that's just my opinion. What do you think? Based on the previous video and this video, what do you prefer? Do you prefer I2C or do you prefer SPI? Please let me know in the comment section and I'll be sure to reply to that. Okay, so that is it, and thank you for watching. Please don't forget to like, subscribe and share, and also leave your comments down below in the Q&A section or comment section below. If you enjoyed this video, please give it a like, and if you didn't watch the I2C video, you can check out this link over here, and I'll see you in the next lecture. Bye for now.